This is problem number 3 on the sample test problems for test number 3. Consider the family of curves with equations of the form f of x equals x cubed minus ax. A, for what values of capital A does f have one or more critical points? Give the x coordinate of each critical point and determine whether it is a local max, local min, or neither. Okay, so critical points means right away we're translating. Critical points happen where the derivative is equal to 0. So let's find the derivative. 3x squared minus a. And we're going to take that derivative and set it equal to 0 and solve for x. So first we'll move the a over by adding it. Move the 3 by dividing. And then finally take the square root of both sides. And when you take the square root of both sides, it is so easy to forget to put something in. And that's this plus or minus. So actually not one, but 2 critical points. All right, so it says for what values of a does f have one or more critical points? Well, it seems like it always has 2 critical points because there's that plus or minus. But then we have to recognize that all the calculus that we're doing is in the real numbers. And so we're not allowed to have any kind of imaginary numbers popping out. And in this case, we have a square root. So there's the very real danger of having imaginary answers here. So in order for that square root to have only real values, we need to make sure a over 3 is at least equal to 0. So multiply both sides by 3, and we get a is bigger than or equal to 0. So for what values of a does f have one or more critical points? For all the a's bigger than or equal to 0. So it says give the x coordinate of each critical point. I think we've done that. The x coordinate of each critical point is given in this formula, plus or minus square root of a over 3, and determine whether it's a local max, min, or neither. So let's try that. Okay, we have choices to decide whether a particular critical point is a local max, a local min, or neither. You can either use the first derivative test or the second derivative test. Maybe we'll give both of them a try here. So if we go with the first derivative test, what we're looking to do is make a real number line. We're going to write down the signs of f prime, first derivative test. And on that real number line, we put all the critical points. And the critical points here were given by our formula. So there's a negative root a over 3 and a positive root a over 3. Okay, and let's see if we're able to pick some numbers that are in each of these intervals. So suppose we pick an x value that's out here somewhere. We'll highlight it in yellow. So I don't know what x value is out there because I don't know what a is, but I do know that I can pick something enormous and it eventually be bigger than that square root of a over 3. So imagine picking an enormous value of x and plugging it in for x. And the question is it going to be positive or negative? So if I pick something super huge, then 3x squared is going to be really big, and then subtract a. Now, a could be enormous as well, but it sure feels like we can pick something even bigger, right? A is some given number. I don't know what it is, but we can outlast it and pick an x that's big enough. So I feel pretty confident that any number you pick out here is going to give you a positive value of f prime. Inside of here, well, there's kind of one natural number. When you say it's a natural number, but it's actually not technically a natural number. It's a whole number. But there's one number that's in there that's kind of natural to pick. 0 is definitely in between these things. So if we plug 0 in to the derivative, we get negative a. Now, negative a could be a positive number or it could be a negative number. It depends on the sign of a. But I think we've decided that the only time we have these critical points is if a is bigger than 0 to start with. So if a is bigger than 0, then negative a must be less than 0. So in between, I feel pretty good that there are negative numbers for the derivative. And then finally, if we pick a number way out here to the left, we're going to pick something super, super big negative and plug it into the derivative. So 3 times x squared, even though x is negative, when we square it, it's going to be positive, and it will be huge. And then subtract a, and maybe a is huge, but again, I think we can pick an x big enough to dwarf the a that's sitting there waiting to be subtracted. So I feel pretty good putting a plus sign out there. Okay, so the first derivative test tells me that the f prime is positive, and then negative, and then positive. And I think that's enough for us to determine whether these guys, these critical points, are maxes or mins. So if we go positive to negative, that means that the function itself, f, goes from increasing to decreasing. So what can we say about that negative square root of a over 3? Is it a max or is it a min? Well, it must be max. And then the function goes from decreasing in the middle to increasing at the end because f prime is positive. So I think what that means is that out here at root a over 3, we have a min. So those are our answers. Negative root a over 3 is a max. Positive root a over 3 is a min. I guess we'll write that down over here. There is one little sticky point here, and that's the question about what happens if root a over 3 and negative root a over 3 are exactly the same number. So we've drawn it so that there's some space in between them. And I guess we assumed that there was, but there is one value of a which would make these 2 points actually smush together and be the same point, and that's a equals 0. And if a is equal to 0, then, well, it's allowed over here. So a equals 0 would actually make both of these critical numbers the same number. And so we'll just put a little kind of a side note here. If a equals 0, then the only critical number, critical point, is x equals, so it's still given by the formula in the box, root a over 3, but in this case a is 0. And so that means that x is plus or minus square root of 0, which is plus or minus 0, which is just a single number, 0. So if a is 0, then there's really only one critical point, and I think we need to do a separate analysis. We can do the first derivative test, but I just feel like the picture we have up there is kind of misleading if a is equal to 0. So maybe we'll put it up here. I think we can squeeze it in. There's f prime. The only critical number now is 0. And again, we're going to plug numbers in on either side. In each of those intervals, we'll plug them into the derivative. If you pick a number bigger than 0, and you plug it in for this x, so let's say you pick x equals 100. So then we're doing 3 times 100 squared. That's pretty big. And then you're subtracting a. Well, could a be big? No, not in this case. A is 0. So the derivative is actually just 3x squared. And I think you can see that then when you plug in something out here into 3x squared, you're going to get something positive. And in fact, when you plug in something less than 0, 3x squared will still be positive. So if a is equal to 0, there's only one critical point. And looking at that sign chart, is it a max or is it a min? Let's see. We know that the original function f, the derivative is positive, so original function's increasing there. Then it's flat for just a moment, and then it's increasing some more. So is x equals 0 a max, a min, or neither? It's actually neither. So I think this is just a separate case we needed to consider. And so we'll add it down here. But if a is equal to 0, then x equals 0 is neither a max nor a min. Okay, so that's fine, and that's the first derivative test. I probably would use the second derivative test in this case. I think it's going to be a little bit easier, so let's give that a shot. Second derivative test is supposed to give us the same information, so let's pretend we haven't done any of the first derivative test stuff. But instead, we're just going to jump down here to second derivative test. And we start with, believe it or not, the second derivative. So f double prime of x equals, so the derivative of 3x squared is 6x. The derivative of minus a, it might be tempting to put minus 1 there, but a is just a constant, and the derivative of a is nothing. So f double prime is 6x. That's it. Now the second derivative test works a little bit differently. We don't actually do a sign chart. What we do is plug the critical points into the second derivative. So I'm going to put negative root a over 3 into the second derivative, and I'm also going to put positive root a over 3 into the second derivative. The question is, are these things positive or negative? So let's see, our second derivative is right there at 6x. So this is 6 times negative a over 3, and that's inside a radical. And down here, it's 6 times positive root a over 3. Okay, now we've assumed that a is some positive number. So what can we say about 6 times this negative radical? What kind of number is that? Well, it's definitely negative. And 6 times the positive version of the radical is definitely positive. And so if we think about the conclusions of the second derivative test, one of them says if the second derivative is negative at a critical point, then the critical point is a, let's see, so negative second derivative means concave down. So I imagine in my mind something concave down, and I ask if that special point is a max or a min. It's a max. And if the second derivative is positive, then we're looking at something concave up. And if there's a special critical point there, then the critical point in this case is a min. So do we get the same conclusions? Let's see. Over here, we said that the negative root a over 3 is a max. Over here, negative root a over 3 is a max. That's good. And then root a over 3 is a min. Agrees with what we said before. What about that funny business over here where we said a was equal to 0? Okay, if a is equal to 0, then f double prime of either the plus or minus root a over 3. Let's see, if a is equal to 0, then this is really f double prime of plus or minus square root of 0 over 3, which is f double prime of plus or minus root 0 is nothing. F double prime of plus or minus 0 is just f double prime of 0. And then again, if we plug into the second derivative right there, 6x, how much is f double prime of 0? Well, let's see, it's equal to 6 times 0, which is 0. So what's the conclusion from the second derivative test when you get 0? And unfortunately, the second derivative test in this case is inconclusive. It doesn't give you any information. So we would have to revert to some other way to figure out if the critical point when a is 0 is a max or a min. Way up at the top, we decided it was neither. Whew. Okay, so all that's done. We'll move on to part B. Find a function from this family with a critical point at x equals 7. All right, so we know our formula for the critical point is this plus or minus, so this is now part B. So the critical point we've already figured out is x is plus or minus root a over 3. I'm looking for a critical point to happen at 7. 7 equals plus or minus radical a over 3. Okay, the square root always gives you an output that is positive, and there's no way to get 7 from the negative part here, so we're just going to scratch that off. And now solve this equation for a, and we will be done. So to solve for a, we first square both sides. The radical goes away. And then finally, multiply both sides by 3. So a equals 147 gives you a critical point at x equals 7. Okay, so this question is done, but it's almost begging for us to look at it a little bit further in something like Geogebra. So again, it's a free download, and you can check this out and just try this on your own. Let's see, so the first thing I want to do is make stuff a little bit bigger. So on my version, that's this font size business. So I have it at 18. You can make something bigger than that if you want. And then I don't like that it's off center, so you click this option right here, and then just in any white space, you just drag and click and drag. And so you can center it. And then what we're going to do is hit this guy right here. It says A equals 2, and if you mouse over it, it says slider. So that's actually what I want. So with that highlighted, click again, any blank space, new window pops up. Let's actually call this one capital A, just so that it matches the problem we're doing. So A is going to range between -5 and 5. That sounds okay, but I actually would like to be able to play around with A is 147. So maybe we'll make it a little bit bigger. Maybe we can go to -200 and +200, and we can go by 0.1s. That's fine. And I'm actually going to change this option in here in slider. The width, I'm just going to make it a little bit wider, so maybe something like 400, so we can see the thing. So there it is. And if I click that arrow, I can then take the A and drag it, and it will range between +200 and -200, so that's fine. And then down here, we just type in our function. So our function is way up there at the top, x cubed minus a times x. So down here, f of x equals x to the third minus a times x. I think you need that times symbol. And we hit enter, and we get that. I don't really know what's going on there. Let's see if we can. Okay, that looks more reasonable. That looks like a good-looking cubic to me. So at a equals 5, we've got 2 critical points. At x equals something and x equals something. Let's get the grid turned on here. So inside of view, you can turn the grid on. And let's see if this agrees with what we had predicted. So we said the critical points were going to happen at at the square root of a over 3. Okay, so let's see if we can plug a nice number in there. For example, if we plug in a is 3, then what's the value of this thing? So if a is 3, then that's the square root of 3 over 3, which is the square root of 1, which is 1. Okay, that's a nice number. So if I move this thing a little bit to the left and jump over to a equals 3, then in theory, the critical point is happening at x equals 1. That's there. And remember, it was plus or minus. So at -1 is the other critical point. And in fact, we can be really fancy here and decide that we're going to plot the point square root of a divided by 3, that's the x value, comma, and then f of that number, square root of a divided by 3. And then it yells at me because I did something wrong. What did I do wrong? Okay, so what I did wrong was not put enough parentheses. So we have parentheses here for the a over 3, that's closed. We have parentheses for the f, but I didn't close the parentheses for the actually plotting the point. So let's fix that by adding one more closed parentheses. And there's a point right there at the bottom. And then we can plot the corresponding point at negative square root of a divided by 3, comma, f of negative square root of a divided by 3. And so we've got our 2 points there. And even as I move a, those 2 points are going to stay tethered to the maxes and mins, the critical points. If it goes off the screen and you want to find it, just click on that guy and then anywhere on the axis and then drag. You can drag it down, and hopefully B and C are still at the top and the bottom. So that's looking pretty good. Okay, so we've got our critical points. That's fine. We had said if A is equal to 147, I think that was our number down here, then we expected a critical point at x equals 7. So let's try that. So if we just slide this thing all the way over to a equals 147, all right, so someplace there. And okay, stuff is way off the screen, so let's drag down. Again, click this icon first. We're hoping to find a critical point at x equals 7. And how does that look? X equals 7, right there. In fact, it has them over here as well. Okay, and then finally, if we start making the a value closer to 0, we should get something funny happening. So let's see if we can make it close, and then we'll zoom in and see if we get what we expected. So let's zoom back in here near the origin. Okay, so still 2 critical points. So far, so good. At x equals 1, we still have 2 critical points. What about at x equals 0? Well, at x equals 0, we had decided, in fact, we only have 1 critical point at x equals 0. And was it a max or a min or neither? It was actually neither, because we were going to be increasing and then flat for a moment and then increasing again. So does that agree? Increasing, flat, increasing. And then finally, if a is negative, we didn't write this, but if a is negative, then that square root gives you imaginary numbers. So what are the critical points? Well, there aren't any. There aren't any real ones anyway. So if there are no critical points, then it won't be flat any place. So let's see what happens if we make a negative. Right now, at least it's flat at the one spot right there at x equals 0. But if I make it a negative, it's not flat at all. It's just increasing the whole time, never ever flat again until we cross the 0 threshold. And so again, you can kind of see whatever you'd like to, but I think that this function isn't going to do anything spectacular. It's just increasing the whole time. So it's nice to kind of confirm all the stuff we do algebraically and with the calculus with the nice software.